Welcome to the Crash Course AP Chemistry Acid Base Edition. So let's get started and cover all the little details that we need to have some success and a lot of success on the AP Chemistry exam. So it's hard to talk about these things in a vacuum because they are interconnected, especially in terms of equilibrium. But very quickly, acids, generally speaking, we like to write the HA so that it has a proton to give, and it likes to dissociate into the protons, we like to call it H plus, and the conjugate base. And there's many different ways you'll see that. And of course, I could write a strong acid like hydrochloric acid and have it dissociate into a free proton and to its, quote, conjugate base. And then I can write a weak acid, and I'll write this alongside it over here, and we'll do, let's say, acetic acid, which is vinegar. So C2H3O2, and it dissociates into a proton and to its conjugate base. Okay, now the first thing you're going to notice as a strong acid, as I'll put over here, and as a weak acid, is that these guys differ in how much they dissociate. Okay, if I'm a strong acid, we don't even consider this to be equilibrium. We would say that this is a completion reaction and it drives and it goes one way. As much HCl or strong acid I have is as much of these ions I have. There is absolutely no equilibrium. But with a weak acid, there clearly is. Okay, so I should write it that way. So it's important that we understand that the strong acid scenario is really no equilibrium. It's a stoichiometric event, meaning as much as HCl I have is as much of these free protons and Cl negatives. Now I say free protons. I could write this another way, okay? Because I want you to understand that these protons is the most simplest idea. To be a Bronsted-Lowry acid, you're a donator. Okay, so in truth, it really isn't free in solution. It's basically donated to the most predominant species in water, and that, of course, is most predominant species in water is water. Okay, so HCl, okay, is written plus water, and this proton, okay, gets donated. That's an example of a Bronsted-Lowry acid, okay? And you're going to make the hydronium ion, H3O+, and of course, you're going to have this chloride ion remaining. And if we're dealing with the weak acid here, the acetic acid, really we have the acetic acid with the most predominant species in solution, and that, of course, is water. And what's going to happen, I'm going to draw a double arrow in this case, is I'm going to make the H3O+ again, the hydronium ion, and I'm going to make the conjugate base, C2, I forgot to put a negative sign there, C2H3O2, lost a positive. So why am I doing this? Well, I'm doing this so we can understand that these both have similar reactions. They're both acids, they're both, okay, proton donors, and I want you to also understand that whether I'm talking about a proton concentration or a hydronium concentration, these are all synonymous, okay, and these are important values to keep track of, let's say in an acid scenario, because they drive our pH downward. Now, what is pH? pH, little p, means negative log. Now, what does that mean? Well, we're going to take the concentration, the molarity in moles per liters of these guys, whether it's H plus or H3O+, again, they're synonymous. And what we do is we put in our calculator, let's say the concentration in an easy way is 1 times 10 to the negative 3. And I put in brackets to show that's a molarity. And when I do a negative log of that, it becomes 3. And what we've done, essentially, is making this exponent positive. And that's what negative log is. And when you have a multiple choice question on the first part of the AP, you'll be given a lot of these. And if you're not, let's say they give you like 2.1 times 10 to the negative 4. A lot of times what you can do, all the times, is make this go to 1, and then you take the positive value of this exponent, and that'll be your approximation of 4, and that would be good enough. So when you're doing the no calculator part of the test, you can estimate and just use that positive value, and that certainly will work. Okay, now, so you understand, okay, if you can get the pH with negative log, well, we can get the POH, all right? And it's an important skill to understand. Now, the POH is not really talked about, but what we do know is that very quickly, this is a review video, if the pH is 3, the POH must be 14 minus 3. And that's how quickly I can get a pH back if I wanted that. So if I want the POH, all right, I can just subtract it and vice versa. And you may say, well, why would I want the POH? I would not want the POH, but you should understand that the pH plus the POH equals the pKw. These little p's are important. Now, what's pKw? Well, we know that when water dissociates, H2O, self-ionizes into H plus and OH minus, the equilibrium expression, Kw in this case, as we've always done, is products over reactants, coefficients become exponents, and solids and liquids do not apply. So you'd put this over H2O, well, we wouldn't put this over H2O liquid because it is a liquid. See, I'm finding my own mistakes when I do this. So this little liquid here is something that I would not put there because solids and liquids do not apply. So we'd wind up with our value like this. So our equilibrium expression, which they love to ask you to write for different equilibrium problems, looks like this. And of course, to get these values into a log, stuff the entire number into an exponent, we can negative log both of these. So this becomes a pH, this becomes a POH, and when you multiply exponents, that's what logs become, all right? The negative log just means convert this to a base 10 log and then times it by negative 1. But these are logs now. So when you multiply logs, you're going to add them. And of course, they're going to add up to the constant. Okay, but they'll add to the constant if the constant has been negative logged as well. So little p means negative log, and this is the pKw. And as we said, the Kw, a famous number, is 10 to the negative 14 at a certain temperature, temperature dependent. So the negative log of this, of course, would be 14. Now, why am I showing you all this? Because a nice thing to do is if you have a hydroxide concentration from one of your problems, then you can quickly get the POH by negative logging it and then subtract from 14 to get your pH. Okay, remember your pH is about this concentration. And as I write H plus, I can also write H plus over H3O plus because they're synonymous. So even though I put H plus here, it could be that. So our pH is dependent upon how much H plus or H3O plus we get. The more H plus I have, the greater the concentration. For instance, this could go down to 1 times 10 to the negative 2. Ah, got bigger by what? 10 times. And the pH now would be 2. So our pH drops as our H plus or H3O plus increases. Okay, that's something you really should have learned. So this is an important skill to have going back and forth and seeing that. Now, getting back to this, okay, strong acid and weak acid, you have to be able to visualize what this really means. If you're a strong acid, let's pretend I have an HCl, okay, let's pretend I have 4 of them, and you put them in a beaker. They're never going to look like this. Strong acids completely dissociate. So what they'll look like if I had 4 of them, or some equal amount, is I'd have this scenario. Now, if I don't have water in there, if I had water in my beaker, and obviously I probably would, it'd be H3O plus. But I'm just showing you that all of these would dissociate, and you would have equal amounts of chloride ions as H pluses. And these are called particulate diagrams. So you have to understand that because of complete dissociation, because this completely goes forward, you're going to have that scenario. That is not the case with the weak acid. With the weak acid, okay, you're going to, if you start with 4 of them, what you're going to have is most of them, what? And I'll just draw them as HAs, okay? Most of them will be completely stuck together with only a little bit of them dissociated. Okay, and I'm going to just stay with what I was doing here, the A. Okay, so the A negative represents this acetate ion or the conjugate base here. So this is A negative. So this is my weak acid. So understand, this barely dissociates. And this is an important understanding in something about Ka. Some people say, I don't know how to do Kas. What are Kas? Well, equilibrium constants, whether it's for water self-ionizing or it's for acids dissociating, are the same thing. Because these reactions here are acid dissociations, we call them acid dissociation constants, but they're still KEQ. Now, KEQ is called Ka when we're dealing with acid reactions, just like KEQ is called KSP if you're dealing with insoluble salts. So, very simple. If you know that you have a strong acid like we have with hydrochloric acid, we know that the Ka is going to be tremendously large. Now, why? Well, because KEQ equals Ka, and Ka is equal to what? The concentration of the products over the concentration of the reactants. If you have a lot of products, which you will have with a strong acid scenario, as I've mentioned, it goes in the forward direction unbelievably well. Why? Because every single one of these dissociates, and therefore there's no equilibrium. It's going to keep going until these run out. So it keeps going in almost every single one of these. So there really is no reactants in that scenario with what? Almost no reactants left and all products. The KQ is going to be very large. You can't even write the number, okay? Very large, maybe approaching infinity, okay? So it's a huge, huge Ka. So the Ka is tremendous, okay? And what does that mean? Complete dissociation because you have all products and no reactants. Now, if we do the KQ here, which again, KQ is nothing more than the Ka of a reaction. Ka if it's an acid reaction. And the same thing here. Ka or KQ or anything is always the products concentrations over the reactants concentrations. So, if you notice here, I mostly have what? Undissociated reactants or acid. These guys barely separate. So I have a lot more what? Reactants and very little products. And when your denominator is big, it makes your Ka very small. Okay? So important, when the Ka is very small, you're talking about a lack of dissociation. Most of this acid remains together, and that's very important. So if I had equal concentrations of a strong acid and strong base, a strong acid and a weak acid, what will happen? What will happen is clearly I'm going to have a greater concentration, a higher H plus or H3O plus concentration here than I would. And therefore the negative log is going to give me a lower pH. So in a scenario where I have, let's say, a 2 molar solution of hydrochloric acid and a 2 molar solution of acetic acid, okay, the pH is going to be lower for the stronger acid because it's going to have more H pluses and in water H3O pluses available. There's going to be a lot less dissociation, so the pH won't be. For a 2 molar solution, okay, the pH will be a certain value, and this would not be as high. Maybe this is, well, these are big concentrations, so I made sure to make my life easier, but this is going to have a much lower pH, and this is going to have a much higher pH, less H pluses, okay? Now we see this in titration curves, okay? If you look at a titration curve where you're going to plot, okay, pH changes in volume of base added. Okay, and let's pretend we're going to add a strong base. Okay, and I'm going to do a strong acid first. We'll do strong acid in blue, okay, or we'll do it in magenta because I can. So the initial pH is going to be low, okay, and it's going to rise slowly and boom, explode exponentially, and then flatten out. Okay, and we know that this point right here, in between where these curves bend, is your equivalence point. And of course, our equivalence point is where the base that I added has now exactly neutralized all of the extra protons, or H3O+. This is where the hydroxide equals the H+ stoichiometrically. Okay, and for a strong acid, strong base, the pH, of course, is 7. Now, what am I getting at here? Well, I started with a what? A low pH if I have a strong acid in my beaker. What I'm doing is I'm adding, for those that don't follow me, I'm adding a strong base, which is in a burette, okay, into a beaker that has my acid. And this is where the pH is 7 because of a strong acid, strong base scenario. Now, if I had a weak acid, weak base, we'll do that in red. It's the initial pH is going to start higher. Why? There's less protons, H3O+, because there's less dissociation. The Ka is going to be smaller. So your titration curve would look like this. It actually would jump up a little bit to make a buffer region. And notice it would actually have the same equivalence volume. Now I'll talk about that. And then it would start matching the final pH. However, where the equivalence point for the strong acid, strong base was 7, the equivalence point for the weak acid, this is the weak acid being titrated, this is the strong acid, the equivalence would be above 7, maybe 8.3 or something. So the equivalence point is now higher, okay? But the point I'm trying to make, and no pun intended, is that the initial pH has to be higher, okay? So it's important that you realize major differences between the Kas and dissociation. Now, before I continue, I want to speak about the conjugate bases, okay? Now, strong acids are strong acids, like I said, because they completely dissociate. And if they completely dissociate, if I have the concentration of the strong acid, I can get the pH very, very simply. Watch. If the concentration of my HCl, let's just make it simple, is 1.0 molar, and I'm not sure why I chose that color, but let's make it 1.0 molar. Let's make it easier than that. Let's do 0.01. Okay, 0.10 molar. Okay, so if the molarity of my strong acid is this, as I just said, because of complete dissociation, this must be the concentration of what? Of my protons. Yes, H3O+, however you want to think about it, whether it's in water or you're doing it this way. That's important you understand that. So the concentration of my strong acid is, yes, the concentration of my H+, which means all I have to do is negative log of this. And you should know this is 1 times 10 to the what? 1 times 10 to the negative 1. So this would be a pH of positive value of the negative exponent of a 1. So if I know the concentration of my strong acid, I know its pH directly because guess what? It has to equal because of complete dissociation. If I've got 1 mole of HCl, because it completely dissociates, I have 1 mole of H+, knowing my volume. Very simple. That, however, does not work for my weak acid. My weak acid does not completely dissociate. So knowing the initial concentration does not directly. I have to do an equilibrium problem to get this value. I got to figure out how much dissociates. Now, why? Why does it completely dissociate? Why can I do this? And the answer here is in the conjugate base. And this is also very important. If I have a strong acid, that means that my conjugate base has no ability to absorb the proton back. This cannot absorb the H plus back, whether it's in water, okay, or from the proton in the H plus, or what have you. It cannot, as we like to say, ionize water. Chloride ions have no ability to do so, partly because they are big ions. I mean, they have a -1 charge, and they're pretty big. They gain an electron and get big. So when you stretch out -1 over a large area, they don't have a great attraction to yank H pluses off of water. And let me explain that. Because what's happening is when you add HCl, what you're going to have is you're going to have Cl negative ions now hanging out with the most predominant species, water. And nothing happens. This negative can't pull the H's off the water. It doesn't. If it did, it would remake hydrochloric acid. And if it remakes the acid, my friends, it can't be a strong acid. So the reason why HCl completely dissociates is because of the inability of the conjugate acid to go in the reverse. And that is why when we get to the equivalence point of a strong acid, strong base, we get a pH of 7. Why? Well, because all the hydroxides are now going to react with the protons that were in the beaker. We're going to make water, and there's nothing else to affect the hydroxide or proton concentration in water, so the pH has to be 7. That is not the case with a weak acid, weak base scenario, as I'm going to mention in a second. Now, if the chloride ion or any conjugate base of a strong acid has no ability, it explains why the acid completely dissociates. There's no what? Backwards. So before I continue, let's go over what your strong acids are. Strong acids you should be aware of. That means that they don't go in reverse, they go forward. Hydrochloric acid, strong acid. Hydrobromic acid, strong acid. Hydroiodic acid, strong acid. Nitric acid, HNO3, and sulfuric are the most common ones that you'll deal with. Okay, so these are, I like to say, the top 5 that you see often. Everybody else, if it's a strong acid, and there are others, okay, they are because of the one they'll tell you. But the reason why is because Cl negative has no ability. Br negative has no ability. I negative has no ability. NO3 negative, which we know is a very soluble ion. Hey, soluble, that means it's not going to what? Reform. And then we should do HSO4, okay? These guys have no ability to absorb a proton back, okay, from water or ionized water, okay, as I mentioned before. So they don't produce any other hydroxides. Therefore, the pH stays at 7, all right? And of course, when it comes to a strong acid, strong base, look at our base. Our base is sodium hydroxide, which is any group 1 ion with a hydroxide. Why group 1 ions? Because group 1 ions tend to be big ions as well. Yes, they lose an electron and get smaller, but they're still a relatively big ion. So their coulombic attractions are weak, and all group 1 ions are soluble. So these completely dissociate as well. So all strong bases produce tremendous amount of hydroxides because they completely dissociate for the same reason that strong acids do. And what I'm getting at is the reason why Na plus is a strong base is because Na plus, which is given off after this dissociates, doesn't do anything. It spectates like NaCl. So at the equivalence point of a strong acid, strong base titration, we have spectator ions. We have Na plus and Cl negative hanging around, and they're not doing anything. So what does that mean? That means they don't affect the pH. They cannot pull H's off of water. The Cl can't grab an H, and this plus can't, okay, produce an acid and pull the negative part. So these ions of strong acid, strong bases are spectators. And the reason, if they weren't, they'd reform the base, okay? So this cannot pull the negative part of water away. This cannot pull the hydroxide away to reform the base. And that's a good thing, because if it did, it wouldn't completely dissociate. And this can't pull the H plus away from the water. It can't do it. And the reason why? It's because these charges, okay, are not big enough and the ions are big. The Coulomb's law states that the charges are not big enough and that the radii, okay, are too big. Okay, too small of a charge and, of course, too big of an ion. Okay, now, so what am I getting at? So, well, what about the weak acid here? Okay, the strong acid, as I mentioned, has no ability, but the weak acid, the reason why a weak acid, okay, is a weak acid is because it produces a conjugate base that, yes, has an ability to reform the acid. That's why you have the arrow back. Very important. So what does that mean? That means that this acid, okay, can pull an H off of water. Let's talk about that. Let's look at that carefully, and let's go to the next page to do so. So when we produce the conjugate, let's write the whole reaction again. So we have our weak acid, HC2, H3O2, okay, and we know in water, this will produce some H3O pluses, not many, just a few, so it does increase. So it does make H3O plus, and it does produce the conjugate base. Now, what is a conjugate base? Because this is going to pop up as well. A conjugate acid-base pair. Okay, that is very important. Conjugate. Okay. So the conjugate, now I got it spelled right, acid-base pairs. Well, this is my conjugate acid, and this is my conjugate base that I, of course, forgot the negative. I have to make sure that I conserve the charge on both sides. So this is my conjugate base. Okay, what you need to understand, these are the what? Same chemicals, and they differ, very important, by only one proton. So this has an H in front, and this is without the H. That's a conjugate acid-base pair, which leads us to believe that this is also a conjugate acid-base pair, and you're correct. They're the same chemical plus or minus the H, okay? And they're based on the Bronston-Lowry definition of basically donating a proton, and of course, for your base, you're accepting it. Now, I didn't draw the double arrow because, as I mentioned, if you're a weak acid with a Ka that's small because you do not produce a lot of products, okay, what that means is you have a conjugate base reforming the acid. I'll say that again. If you're a weak acid and you barely dissociate, it's because the conjugate base has an ability to reform the acid. Well, what would that look like? Well, you would take your C2, H3, your conjugate base, your chemical left over after it gave it off. So this barely becomes this, but when it does in this reaction in water, okay, this will also happen in water. So this negative conjugate base, it's the same chemical, I'm just rewriting it, in water does what? It has ability to yank an H off the water to reform the acid. And in this way, you remain a beaker full of undissociated, mostly undissociated acid. As soon as some of this goes forward, okay, this conjugate base reforms the acid, does this reaction in water. And that's why there's a double arrow here. Okay, now when it does so, though, notice when it pulls an H off, it's going to make a hydroxide. So not only does it reform the acid, okay, it produces a hydroxide. So it's very important you understand that weak acids, their conjugate bases have an ability, a decent ability to reform the acid, which is the reason why they are weak. That's the reason why they don't go forward that much, because the reverse happens. Strong acids, there is no reverse. The conjugate bases don't go back. But the big difference here is that at equivalence, at the equivalence point, let's go back here, at the equivalence point of a weak acid, strong base scenario, at the equivalence point, the pH is greater. Well, why? Why is the pH greater? Well, when all of the all the acetate ion, or acid here, reacts with the hydroxide, and let's do something called a Stoick Table. At the equivalence point, okay, strong base is added, and let's just say that there is 1 mole. Let's make life easy for ourselves. Okay, initially there's 1 mole of C2H3O, the acetate ion, the acetic acid, the vinegar, a weak acid, easy for me to say, in the beaker, and then at equivalence point, I had to add 1 mole of the hydroxide. Absolutely 1 mole. Okay, that's what equivalence is. And you say, Mr. Grotsky, wait a minute, this barely dissociates, but very important, this strong base will force the hand, will force all the weak acids to act like a strong acid. So in water, this barely goes forward. Barely. The Ka is extremely slow. But with a strong base, it forces all of this, okay, to produce our weak acid, our conjugate base, I should say, C2H3O negative. It forces its hand stoichiometrically. As much moles of base do I have is as much moles of conjugate base. So this was 0 initially. Okay, now I know, of course, it makes water in this reaction, but we don't care about that. It's a liquid. All right, so what happens is the change is I'm minus 1 mole. Why am I minusing a mole? Because I have enough base to force it forward at equivalence. That's what equivalence is. So I'm minusing a mole here. And here, I plus 1 mole. That's the catch. Okay, all of this base drove all of this to become this. So we always say 100% of this is now gone. Okay, now this went to 0%, and now it all came to conjugate base. So as much weak acid I have now, that's how much. So I lose exactly a mole because I had a mole of base to drive it forward. So all of this became this, and that's why I add a plus 1 mole here. So at equivalence, these guys neutralize themselves. The strong base forced this to become this, and the base grabbed the H to become water, so these guys don't exist anymore. So at the equivalence point, I have 100% of the conjugate base. Again, initially, what do we have? 100% in the beaker of conjugate acid, right there in that titration. That's what I have right here. And then when I get to the equivalence point, which we see that it's way above 7, we'll talk about that. Now I have 100% what? Conjugate base, and 0% acid remaining because all the base that I added drove it away. And this is the catch. Once I have this base, why does the pH go above 7? Well, because it reacts with water that's remaining, and because it has ability to ionize water and pull H's and hydrolyze water, it produces hydroxides, which pushes your pH higher. So there are AP questions that ask you, hey, what is the final pH? And you'll figure out exactly how many moles of conjugate base was made by knowing how many moles of the base was added to match this. Then you're going to divide the moles by the total volume of the solution at this point. What's the total volume? Well, we have maybe 40 milliliters of base were added into a beaker that had 40 milliliters of acid. Maybe it's 80 milliliters. So I divide that by 0.08 liters because molarity is moles over liters, and I'm trying to get into molarity, okay? And once I have that concentration, okay, I can do an equilibrium problem here and set up my initial concentration. Okay, these would be 0 and 0, and this would be minus x plus X, okay, as we've done before probably, and then whatever the initial concentration is, minus X plus X, and what you would come up with, okay, in your equilibrium problem, the value of your Ka is equal to X squared over this concentration. Now, really, okay, if I do my math, let's go find that number, it'll be, and again, this is a review video, that's why I'm kind of quickly go over the equilibrium problem, but 1 divided by 0.08 in my example is 12.5. That's kind of a big number that I made, but in any case, I'll live with it. 12.5 molarity minus the X, but the X is going to be tiny, right? Because the reaction barely goes forward or backwards because the Kas are so small. That's an insignificant, so we always take that off. If you have this value, okay, you can solve for X, square root both sides, and the X that you get is going to equal either this concentration or this concentration. And guess what? If it's the hydroxide concentration, I would negative log my X to get a POH. And then 14 minus that would give me my pH. And the bottom line is the reason, if they just asked you to explain, a lot of times they'll just say, explain why the pH is higher in a weak acid, strong base scenario. And you would say because of the hydroxide that's produced from the conjugate base left over that does what? That hydrolyzes water, splits water, or pulls protons from water. Okay, whereas a strong acid cannot do that. Now, of course, we can have titrations that go the other way. Okay, we can have a titration where we have a strong, a weak base, okay, and a strong acid. So a weak base and strong acid would do something like this, and it would crumb down, and then scroll down. And if I do this correctly, the equivalence point would be less than 7 here. And you say, whoa, 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 whoa. So if I have a, whoa, 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 whoa. If I have a weak base, but a strong acid, and I'm basically adding, no pun intended, a strong acid into my weak base, notice I'm going down now. So in my beaker, in this case, you'd have the base and the acid being added. The equivalence point would be below 7 because if you guessed it, the weak base will produce a conjugate acid that will be able to do what? Well, the conjugate acid will be able in water at the equivalence point to do what? To push its its proton on water to make H3O plus and therefore drive the pH down. So where the AP is going a lot, they're doing less calculations and more explaining. You should be able to explain why the equivalence point is at 7 for a strong acid, strong base, and why the equivalence point is above 7 or below 7. And it's all about the conjugate acid and conjugate base that's made for the weak base of weak acid at the end. If it's a strong acid, strong base, as I said, the conjugate acids and bases of them don't do anything with water. But weak acid or a weak base will produce a conjugate base or a conjugate acid that will hydrolyze water. That's really important. And again, they're doing less calculations and more explaining of things. All right, so that's a major understanding. Now, if you noticed in my 3 titrations I drew here, we all had the same volume, the equivalence volume, and that's a definite strong possibility, assuming that the acids. So this weak acid could be a 0.1 molar scenario as concentration, and so could be the strong acid, yet they still can have the same equivalence point. And the reason is, again, the strong base can drive off all the H pluses, even though the weak acid barely dissociates. Okay, so those are some serious points to consider when you're doing strong acid, strong basing, doing acid-base equilibrium problems. Now, let's talk about a buffer, because buffers are big parts of these types of problems. Now, here is a terribly drawn graph, but let's do my pH again, and let's do the volume of a strong base added. and let's make some sense of this. Okay, now, if I have a weak acid, which initial pH is going to be high, and it kind of makes a buffer region, and then it shoots up, and there we go again. We're going to have our equivalence point here, and as we said, weak acid, strong base, my pH is above 7, 8 point something, and then if this represents 40 milliliters, that's exactly how much base was needed to neutralize all of the protons from the weak acid with the hydroxides. Then you need to realize that at 20 milliliters, I'm at the halfway buffer position. I'm at halfway titration position. I'm halfway, which means at this point, if this is 100% conjugate acid and 0%, okay, conjugate base, A negative, at this point, I have 0% HA. All of it's been forced away. We've talked about that. And I have 100% A negative. We talked about that. But what's this position? In this position, we're halfway titrated. What does that mean? Well, if I have my acid HA and I drop the base, as sometimes I do on the weekend, okay, I'm going to pull H's away and I'm going to make water, as we've talked about, and I'm going to make A negative. We've seen this before, okay? But if I have 1 mole of acid in my beaker and I only add 0.5 moles for my solution, this is the limiting reagent, so it's minus 0.5 moles, right? This is what drives the weak acid. This is a weak acid. And this is 0. This is going to be plus 0.5. Look what I have here. The base is completely gone, and now 1 minus 0.5 is 0.5 moles of my acid. And I have 0.5 moles of my base. I have equal amounts of conjugate acid and conjugate base. That's why I would say here there's 50% HA and there's 50% conjugate base. I call this the max buffer solution. No one else does. Now I call this max buffer because we made a buffer. We have a conjugate acid base pair and we have equal amounts. What does that mean? Well, we do know that as high as the Ka is for the acid, the Kb for the conjugate base is low. I'm not going to derive that, but we should know that Ka times the Kb of the conjugate base equals Kw, which is 14, or 10 to the negative 14. All right, why does that work? As strong as the acid is, more products, more ions, weaker the conjugate base. Hey, we learned that. Stronger the acid. When you have a strong acid, your Kb is essentially insignificant. But when you got a weaker acid, the Kb gets stronger. So if the Ka is small, the Kb gets bigger, which means that the conjugate acid-base pair cannot neutralize themselves. So when you create a buffer by half titrating each other, or you don't have to be half, but in this region is the buffer region where you can actually buffer acid and base. So if I was to have HA, which is a weak acid, and I was to have A negative weak conjugate base in a solution, if I drop a base, okay, this base will get neutralized by that acid, and if I drop an acid, that would get absorbed by the conjugate base. So if you've got a buffer set up where you have a conjugate acid-base pair, important, if you've got a buffer set up for a conjugate acid-base pair, then what do you have? You have a scenario where you can absorb. So they'll say, hey, if I drop some acid or base on this scenario, what's going to happen? You'd say the pH won't change much because you have a conjugate acid-base pair that you have some acid and base that can both absorb some amount. Now, eventually, it's not perfect, as you can see in the titration curve. Eventually, it gives away as you run out of one or the other. So it's important you realize what a buffer is. A buffer is a conjugate acid-base pair of the same chemical. Now, what's really cool is that, and they're going to ask you this, they're going to know what pH I can buffer at. Now, it's important that the max buffering position, this halfway point, gives us something pretty magical. And this pH that I measure from this buffer position is equal to something called a pKa. What the heck is a little p? Negative log. And what does that mean? That means, my friends, that if I know my pH of the max buffering position, which is the halfway neutralization point or titration point, okay, always, I can solve for the Ka. How do I do that? Well, the pH equals the pKa because in the Henderson-Hasselbalch equation, we know that the pH equals the pKa plus the log of the ratio of the concentration of the conjugate base available over the ratio of the conjugate acid. And if you know, my friends, that if you have equal amounts of these two in a scenario like this becomes the log of 1. And the log of 1 is 0, and it becomes the pH equals the pKa. What does little p mean? P means negative log. So if I find my pH, I know it's my pKa, and to go from a p back to an actual number, we do 10 to the negative value. So if the pH, let's pretend it's 3, that means my pKa is equal to 3. So if a pKa is equal to 3, to get my actual concentration, or my Ka I should say, I do 10 to the negative 3, which is 10 to the negative 3, right? So this becomes 1 times 10 to the negative 3. So I can actually get the Ka of my acid at the max buffering position. But more important, if you're trying to figure out who is a good buffer, what would create the best buffer solution, you look at Kas. If I've got a Ka, that's 1 times 10 to the negative 3. What do I know? Well, when it becomes a what? pKa. I take the positive value. The pKa, negative log, is equal to 3 for the same reason why the pH, okay, would be 3 if the hydroxide, the H plus concentration was that. And what does that tell me? It tells me that I have the acid that produces this Ka would have a good buffer region around a pH of 3 because I have a max buffer position there. If I've got a Ka of an acid equal to, and I'm keeping the numbers simple, 1 times 10 to the negative 6 for the acid, its pKa is equal to what? 6, which equals the pH of the max buffering solution. In that scenario, I'd have a buffer in this range at 6. So if they ask you which of the following creates a buffer solution at a certain pH, you look at the Ka of the acid and do the negative log of it. Find that positive value, whether it's in the part 2 or easy ones to estimate in the multiple choice, and that'll tell you the best buffer region, okay? And the last little piece and I'm done. At some point in your career in chemistry, you used chemical indicators that changed color on this asymptotic region, and you're able to estimate this volume that you're adding. If they're asking you to pick a chemical indicator that best works, they're not going to give you a pH range. Guess what? They're going to give you either the Ka of the acid-base indicator, which means that the acid-base indicator is a weak acid, weak base equilibrium. Right, indicators are weak acid and weak bases. So if they give you the Ka or they give you the pKa, which is nicer, okay, let's say phenolphthalein, that turns what? Pink in the presence of a base. Its pKa, and I'm off the top of my head, is probably 8 or 9. Let's make it 9. What does that tell me? It tells me that the color change for phenolphthalein will turn pink and buffer around this region. Here's a buffer region. So if I'm titrating, okay, make this thicker. This is my titration line, right? And then phenolphthalein will actually buffer in this region. So it'll change color from clear to fuchsia or pink. It's also getting titrated, but it's such a small quantity, it doesn't affect your results. So you want to pick the pKa, okay, that buffers in the region where you have this asymptote. And the general rule is pick the pKa that's plus or minus 1 from your equivalence point. So if your equivalence point is a pH of 7, pick one where a pKa is 9 above or 7, and that's a safe bet. The pKa is really the pH of the max buffer position. And indicators, okay, sometimes they're written like this. H of an indicator is also an acid-base equilibrium with its conjugate base, the indicator negative, okay, plus the H plus. And they change color, okay, in the presence of an acid scenario or a base scenario. So they're really acid-base pairs, so they have Kas. And you can do negative log of it, or they can give you the pKa, and you know it equals the pH of its max buffering position, which has to be plus or minus within the equivalence point. So if I know my equivalence point is 5, I'm going to pick a pKa of my indicator to be either 4 or 6, and that would be nice and appropriate for a what? A color change to occur, because again, this is an acid-base indicator that's buffering and changing in that region. So these are some of the skills and tools you need. I did not specify and go over much of equilibrium problems. I'm assuming you can do that, but this is some serious understanding of what's going on. And you really need to visualize what's going on, because they're going to ask you to have particulate diagrams. I hope that was helpful.